Hi there, this is Dave Tabb, and this is the second of my little training videos on how to do top-down proteome informatics. For the purposes of this project, I'm just doing a simple set of 6 raw files that were collected in the Chameau-Roux laboratory here in Paris, France. And I'm going to show you the use of pTop to make sense of these data. A lot of people, I think, are familiar with ProCite, particularly for Proteome Discoverer or Topic. pTop, I think, has received relatively little exposure outside of China, and I wanted to see that other people knew about it. Why do I recommend pTop is a good tool to complement what you already have? I would say, first off, it's free, and that is a really big plus when you're trying to do data analysis at home and are away from a computer that is actually licensed to run some of the more expensive software options. Secondly, it's Windows-oriented, which means that you don't have to learn how to use the command line or heaven help you Linux in order to make use of it. It's also very fast and pretty darn sensitive too. So I feel like it offers quite a lot to make your day easier if you are working in top-down informatics. I wanted to specify that I'm working with version 1.2, which is not the pTop 2 release that they're currently working toward. I would say that the software development on pTop is at the moment not really in motion. So if you want to download a tool that isn't going to be changing every week, pTop 1.2 is actually a pretty good option for you. So I'm going to walk through each of the settings that appear on the 3 screens. This is a 1, 2, 3, go kind of interface. So it's a pretty quick way to make sense of your data. You don't need to answer a lot of questions to deal with that. In this case, I would note that we have a variety of input formats that we can work from. I've only done testing for raw, and one of the reasons for this is that pTop does quite a lot of data analysis, low-level data analysis itself. So being able to do peak picking and monoisotope finding and so on itself really helps this software. So starting from raw data is a very good thing. Naturally, if you're starting from an instrument type like a Bruker or a SciEx, then you wouldn't have this option because it doesn't have direct reading of those formats, I believe. The next thing, and this should be reasonably obvious but isn't necessarily, is that you need to know what kind of activation was used to produce fragment ions in your top-down spectra. There are some tools like Topic that will automatically detect from your raw data what type of activation was used, but that is not true of pTop. So in pTop, if you specify that you are dealing with a pile of ETD data, as I have here, and feed it HCD raw files, it will complain that it gets no spectra. So be sure that you specify which one is actually present in the files. Now these files kind of put us in an odd middle place. As you can see, they come from PXD 019247. It's a published data set, just E. coli shots, so nothing terribly remarkable there. But these spectra were collected using ETHCD, which used to be called, I think, ETD supplemental activation, which is to say that the initial breakage of peptides was carried out through, by creating a radical, effectively. So you get C-Z pairs, and in some cases, those a complex of the C-Z pair has been kind of tickled apart with a little bit of RF, basically, a little bit of HCD. So the resulting fragments should be dominated by C-Z pairs, but there's some possibility that there will also be B-Y pairs. In this case, I'm simply going to specify that they are ETD and hope for the best, because it's certainly a lot better to treat spectra like these as ETD rather than HCD, even though both elements are somewhat reflected here. All right, so I've now specified my raw data that they're ETD. I've provided my files through this little add dialog that pops up if I click add. Of course, if these were not the files I wanted to process, I could click clear and load up another set, no problem there. The software kind of remembers what you did the last time you ran a search. So if you are doing a new data set, you're going to have to make sure that the settings reflect the new data set and aren't simply carried forward from the last time you used the software. Okay, for data extraction, you can see that these are collapsible options, but I want to point out that I've already made a really, really big change here. You see that I've unchecked mixture spectra. This software is designed to detect whether there are multiple precursors in the isolation range used to produce the tandem mass spectrum. And because many of the peptide ions or proteoform ions that we deal with are at a very high charge, an isolation width of, say, 1.5 m over z is actually really, really wide when you multiply that by, say, 22 charge. Something like that can lead to a lot of different precursor ions all coexisting in the same space. So in this case, I've turned off mixture spectra so that the software will not attempt to identify tandem mass spectra to multiple precursors. That is a really big change, and it is not how the software is generally tested by the authors of pTop. But if you need each spectrum to have one and only one interpretation, you had better turn off that mixture spectra option. All right, you can see that things like maximum charge and maximum mass are here. Certainly, if you're dealing with proteins that are quite large in size, you'll want to increase that maximum charge size. But there is some question as to how effectively those precursors will be recognized if you increase this to, say, 60 or 80, for example. But in general, these options I've all left just as they were when I installed the software, except for the mixture spectra option. The software was generally tested on high-resolution data from thermo instruments. You can see that we expect to know intensity values to fewer degrees past the decimal place than we do mass charge values. And down here at the bottom, I want to note that there's this other window showing the output from the process that's currently running. I've kind of collapsed that down, but I didn't want to just hide it away from you. All right, let us roll back up to the top. Now we want to move over to the identification tab. And this comes to a spot where we need to answer some questions about what search space should be considered when making sense of these data. We start with the fact that we need to specify a sequence database. Now I have a few different ones on here, and in this case I've used a bottom-up derived sequence database. I started with all of E. coli, but I ran the bottom-up data that were associated with this entry against that sequence database, and now I've got a half-size database that includes only about 2,000, I think, proteins from E. coli that were hit in bottom-up. This has the benefit of making my search run faster here, but it also has the disadvantage that if a peptide from the protein doesn't appear in bottom-up, I've got no chance of identifying it in top-down. The precursor tolerance, as you can see, is quite loosey-goosey at 2.2 Daltons. This reflects the fact that we frequently have quite a lot of masses possible falling within our isolation width of 1.5 or 2 or 2.5 m over z. So leaving this rather loose is valuable. But you do see that we're using a tight mass tolerance for fragment ions of 10 ppm. I believe by default the software specifies that just 2 PTMs are allowable, but as you'll see down below, the modifications I'm choosing do not typically cluster up where there's a whole bunch of possible modifiable sites in a protein. So I've upgraded that to 3. I've also run some searches with 4 PTMs per proteoform. You probably don't want to set that to 10 because that's likely going to lead to all kinds of odd behavior, but certainly if you're running a search like a phosphoproteome, attempting to do up to 10 modifiable sites on the peptide is likely to just run you into a space where everything's a false positive, essentially. So we have to be kind of careful that this number is high enough, but not too high. Where that sits is a little tough to know. The cost of setting it too high is not just a slow search, it's also one where you've compromised your specificity. Okay, let's go to modifications. As you can see, I have 0 fixed modifications. Now, if you're from the bottom-up world, that might seem really weird. After all, in the bottom-up world, we very frequently make use of iodoacetamide, therefore our cysteines don't have a mass of 103, they have a mass of 160. But this is the top-down world, and in the top-down world you cannot expect that everyone is going to make use of a fixed modification. So in this case, there is no use of iodoacetamide or iodoacetic acid or of MMTS. So our cysteines are, as they were born, 103 Daltons. We do, however, have a couple modifications that we're going to take into account. It is certainly worth your while, if you are dealing with top-down proteomes, to include acetylation at the N-terminus. Now, if you're used to doing this in ProCite Proteome Discoverer, acetylation of N-termini is turned on by default. You don't have to turn it on there, and in fact, you don't even see that option if you add the advanced options in ProCite. But here, in pTop, we must specify manually that we want to look for acetylations at protein N-termini. Very important piece to include there. And also, I would note that it's really kind of zany to assume that all proteoforms will lack any methionine oxidation. If you think about it, if you have even 4 methionines on a proteoform, and each of them has a 1 in 5 chance of being modified, the chance that all 4 are not modified is, sorry, I gotta think about this, is 80% for each one raised to the 4th power. So that's 0.64 times 0.64. It's not a high number. You want to retain sensitivity for proteoforms where even one of the methionines has become oxidized. So it's very important to include oxidation on this list. As you can see, any one proteoform will be limited to a total of 3 modifications. And at least in pTop, it appears that both acetylation and oxidation count against that list. So it may not be treated, acetylation may not be treated as a counted modification in other tools. Here, I believe it is. You can see, of course, that there's a very long list of identifications here. That's not to say that everything you want to deal with is in here, though. What if you were looking for glutamatylated peptides? For something like that, you would need to display all of the modifications, and then you can go hunting through this massive list to find it. So it's kind of nice that they've created this option to limit to the things that people frequently search for in their search dialog. Down here, we have just one question to answer about how we will filter our results. The sequence database we provide contains only target sequences. It does not contain decoys. But the software will create decoys in silico as a way to compute what the false discovery rate is. And it does that empirically. So it's important that you filter to a particular false discovery rate. We're going to leave that at 1%. We come over here to summary, and we get a nice wrap-up of all of the things that we've told it so far. We see that we're running with raw format, using ETD fragmentation. These are the names of our raw files. The isolation with the mixture spectra, all of that stuff is showing up right here. I don't think there are any options that show up here that are not configurable at an earlier stage, but it's good to see that this is all here. We can now click Save to save this configuration. The next time I launch pTop, these options will all be here by default, including the raw files. So if you plan on searching the same data set lots of different ways, that can save you a lot of time and just modify the one parameter you want to change. But after that, it's time to click Start. So let's click Start, and now that output window at the bottom is going to be where all the action is. And here we see that the output window is already starting to generate little lines of output to show us what's going on. The software is not inherently graphical. The tools that are running behind the scenes are receiving these options on a command line of sorts. Here you see that pparse is doing a lot of work on our behalf right now. pparse is the tool that handles deconvolution and I think deisotoping as well of the ions that are observed in MS scans. And I suspect they have it doing that same project for MS spectra as well, unless it's being handled in pTop. I'm not sure of where the division of labor lies there. And it uses a tool called extract, or pextract in this case, in order to pull the data out of the raw file format. Now, I wanted to note that it specifies that this software is going to expire on January 1st of 2100. pTop is free software. You can download it and install it for free, but it is licensed software. When you download the software, you must send in, the first time you launch the software, it will ask you a set of questions about your institution and so on, and then it will ask you to email that information into, I think, pTop at the institution. I actually found that email address was not being monitored, so I sent it to my friend Chi Hao at the Institute for Computing Technologies. So when I received my license in response, the license is a document I have to then import into the software, and after that, it just is happy as a clam to do anything you want. So the software is licensed here to run until the year 2100. So if you are a newborn babe right now, this software will run probably most of your natural life. And that is a nice feature to have in software. You don't have to pay them a certain amount of money every year. As I said, the software license in the first place is in fact free. So they like to know who's making use of their software. And that's really good for them, because that way when they apply for government funding or from grants of more typical types, they can say, look, people all over the world are making use of our software. So definitely, I think writing a quick email to the folks to say, hey, can I license it for this machine? Here are the details you asked for, and getting it back is a very nice exchange. It works well for them, and it works well for us. As we see, the first of the raw files has now been extracted, and I think pparse is starting to work over the data set there. So it started in the binary format in a raw file, and then having pulled the raw data out into into MS1 files, those MS1 scans can in turn be worked over. So if you were to look at the directory where this is running, you would note that it's rapidly filling up with a bunch of files. So if I pop down to my drive D here, and I pop over to projects and kick into this particular project, here we are, E. coli, and I go to the top-down directory, I see that a whole bunch of stuff is accumulating in here, MS1 and MS2, PF1 files, and so on. These represent the software's intermediate files for processing this individual raw file. So that's an important thing to know about. If you're going to be running multiple top-down search engines, keep in mind that each of them is probably depositing some sort of intermediate in the directory containing raw files. All right, now I'm not going to continue this video all the way through to the end. Instead, I'm going to stop it right here. You can see that the software is going to do a fair bit of time on pextract and on pparse top-down. Yes, here we see that it's finished doing the deconvolution for for the MS1 scans. Here it's begun the scans for MS2, but it's going to take some time to do this. So I will come back and shoot another video when this search is finished, and then I can walk you through how to interpret the results that come out at the end. All right, thanks a lot, and see you soon. And welcome back to the demonstration on how to deal with pTop results, and how to use pTop in your top-down database searches. Through the magic of computing, I have transported you to a moment when our search has finished. Now, I have all of these output files that came from the software. I thought it might be worthwhile to try to walk through them. First off, these top 6 directories all represent individual raw files that have been that have been searched, and each one of these contains our identification. So much of our video is going to pertain to how do we interpret the results that come back from those directories. But for now, I wanted to note that there are a lot of bits of information recorded that came from pparse and the other aspects of this pipeline. I think many people understand that MGF files are intended to communicate tandem mass spectra to search engines. I believe that these MGFs represent the deconvoluted spectra after pparse processing, which is awfully valuable. There's also information recorded in tabular form to describe these individual raw files in the CSV files. These are not search results per se, but they do tell us about the spectra that we collected. So if I were to open one of these, I can simply double-click on it because my software, my Excel software knows that CSV files are comma delimited. Here I see what kind of activation was used, what kind of instrument type this represents, an ion trap, although I think that this was carried out in a Lumos. The MS scan numbers, the original precursor mass to charge value, the charge state at which it was characterized, the total number of precursors, the precursor identifiers, etc. Now, we told the software, don't look for multiple precursor ions for these individual tandem mass spectra. So the total number of spectra should be fixed here to 1. What is the charge here versus this charge? I believe that these represent cases where the instrument captured a different precursor charge at the time of data acquisition, than the charge that was perceived by the pparse software. So if we skip down through here, we can get things. We can get an appreciation for what the likely charge state distribution is for the raw file. So it's something that we wouldn't want to just bypass and say, well, that spreadsheet doesn't have proteoforms in it, so why should I care? Okay. As we continue down here, we see that the MS1 file, and I think the MS2 files, yes, that were produced by pextract along the way are included, and we have pf1 and pf index files and pf2s and so on. These files I know much less about how to interpret, but they have been at least indexed to allow for a very, very quick search. We have raw info files. I believe that these are text, if I remember correctly. They have some information about the origin of those raw files. The extract reports are here as well. Okay, but as I said, I'm probably most interested in what was identified from these files. So if I come through here and click on a particular directory, I see that I'm going to receive a plabel file, a configuration file, a comma-separated values file. This is the magic one for us. A query file and a summary. So these are each going to have different kinds of information to present. If I were to look at the config file, for example, I would be reminded of how I set up this search. Oh goodness, go away. There we go. So if I pull over config, I see that this is how pTop was configured. It says I am pTop version 1.0.3. It's a little confusing because sometimes we see a version number of 1.2 and other times the subunit parts have different version numbers. We get to see how the MSMS path was set up for doing the pTop run itself, what sequence database was used, because yes, even experienced informatics people forget which sequence database was used for a given search from time to time. We have information about the format, the precursor tolerance. These are all things that were captured in that original user interface. No fixed modifications, but we do have oxidations and acetylations. Great. So those are useful bits of documentation to help us remember what our search entailed. But the business end of this is in search task. The search task file has been filtered to achieve the specified false discovery rate that you provided. In our case, we said 1%, and that's what the software has attempted to create. So let's go ahead to open that sheet in Microsoft Excel, or any worksheet will do any spreadsheet will do just fine for this purpose. Naturally, you're going to want to be able to relate these particular proteoform identifications back to the spectra that they came from. And in this case, we see that the raw file name is everything up to this first period, and then they're using kind of an old DTA style file name specification to indicate the scan number within it. So this is scan number 2702 out of this raw file. And in this case, they're specifying that the charge date is +10. You can see that that information also appears over here. So you can get quite a lot of information just out of what's called the title within these search results. We have a precursor mass and a theory mass. Do you see those both? These numbers are going to differ because the theoretical mass relates to the identification that's been applied to this spectrum. So we'll see what that is down here. We see that the mass difference on the mass scale is 0.008. We also get to see it on the ppm scale, which is an awfully nice feature. Sometimes you want to do your filtering on the basis of precursor mass difference in Daltons, and sometimes you want to do it on the basis of ppm. So both of those are present here. We don't have a huge number of columns here. It's one of the nice features of the software that it protects you from all of the going into the weeds of having a bazillion different configuration options and bits of feedback. So it's kind of a simple output, and I rather like that about it. The number of matched peaks appears right here in column H. We see that there are 106 fragment ions that buttress this particular proteoform, and a score, 148.52. How do you interpret the score? I think it's safe to say that we prefer a high score to a low score, but is a score from the top spectrum comparable to a score from an entirely different spectrum? No, I think that the authors would argue you shouldn't. These proteoforms are listed in an ordering that reflects on our confidence in them. But you see that the score column is not what they're sorted by. 123 is a lower score than 140, and yet it's ranked at the second position. That's because these are actually sorted on the basis of e-value. A lower e-value means that it was far less likely to have produced a match this good by random chance alone. And that is different than what the score should be interpreted to mean. So use the e-value to determine whether you're going to trust a particular proteoform or not. Okay, how is a proteoform communicated? We start with the fact that the accession from which this proteoform was derived shows up in column J. One of the things I like here is that they do not truncate off everything before and after the two pipes. I've seen some search engines that would simply say P0A7M2 and throw away the rest of it. But personally, I like to have that option up to me. If I want to parse this part out, that's great. But in this case, the software leaves all of it in there. So that's very good news. I didn't mean to have my Teams running. Sorry about that. Okay, so we come back over here and we see that the accession is here, the sequence information is here. You might think, why do I have to include the sequence? I've already got the accession number. But the reality is, a proteoform may easily be truncated. You may have more than just the initial methionine cut off after all. So we need to be able to know what is the sequence of this particular proteoform itself. Over to the right, we see that there's also information about which PTMs are there. What the software is giving us is the location within the proteoform that this particular modification appears. So it appears at the 55th position in this sequence. If we count from 1 to 55 across that sequence, hopefully we hit a methionine, because that's the only thing that we've allowed to be oxidized in this case. The oxidation, I think, is the HupoPSI interim name for this modification, and the specificity there says that it's allowable on a methionine. Okay, so we see that we have e-values here that help us to know how confident we are in these. We have a fair number of null values that appear in column L. The null values are going to represent those proteoforms in which there was no modification detected. All right, so if we were to look at just the PTMs, I can blow out that column. We see that we allowed, I think if we recall, 3 different post-translational modifications per peptide. But we see that generally speaking, the software did not make use of that many. The most common case here was probably no modification, but sometimes we see 1 modification, sometimes we see 2, and sometimes we see 3. An odd aspect of the way they do the reporting here is that every modification is always followed by a semicolon. So if you were to simply count how many times the semicolon appears in column L, you could also sort these identifications by how many modifications they contain. Alright, so as we flip down here, we see a few of these that have 3 oxidations. Oh, quite a few more as we get down to that part. You can see that if I had just done a search where only up to 2 modifications were allowed, all of those triply oxidized peptides would be missing. So that would be kind of disturbing to me. I don't want to lose those identifications just because I didn't want to take a little extra time to do the search. And as I said, the software is relatively quick. I think it's reasonable to assume that for most search databases of 6,000 or fewer proteins, a given raw file is going to take less than an hour to search. In this case, I had 6 raw files searched against a database of 2,000 some entries, and I believe all of it was done in a couple hours, if I remember correctly. Here we see that sometimes those acetylations are also appearing. You'll note that acetylation does not show up as being on the first amino acid, but rather on the 0th. And that's a really important convention to understand, because here the acetylation is taking place on the amide, not on the side chain of that N-terminal amino acid. So a position of 0 is the correct way to think about where the acetylation is connected, not the first side chain. Okay, well, so that's our long list. When we get down to the bottom, we see that the software has cut off 3.08 times 10 to the negative 4th power as its expectation value score. That's the lowest it accepted. So the software made that judgment on the basis of the false discovery rate filtering that was put in place. All right. So I think that's everything I want to show you for now. We showed how to search the results. We've shown what kind of files result from them. And I hope that you've come to realize that this is a pretty handy tool if you're trying to get a rapid bit of feedback on whether the top-down experiment you just conducted went okay or not. You could set it up to run through some of the more time-consuming pipelines, but I think that pTop actually does a really good job of giving you quick results that are easy to interpret and easy to configure and launch the search. And even better, it's totally free. I can hardly turn down a piece of software that I don't have to pay for. So I hope that's been useful to you, and good luck with your top-down data analysis. Oh, I would also like to say thank you to the Epic XS project for funding the training videos that we're doing up here. Thank you very much.